Welcome back. We finished with erosion, which is the movement of sediments like gravity, wind, water, glaciers. And we're going to now move on to the deposition of those sediments, settling them down somewhere, placing them somewhere, depositing them somewhere. And we're going to do this by looking at the vocabulary of deposition in relation to glaciers, gravity, moving water, streams and rivers, the ocean, and the wind. And the wind, there's a word I'd like to introduce here that describes the erosion and deposition of sediments by the wind, and that is aeolian. So you don't need to know that word. They wouldn't be used in a test or something, but it's a nice word. The aeolian deposits, wind-borne deposits, aeolian erosion. And all of this is covered in chapter 19, incorrect on the slide here, chapter 19 of the review book. Before we get into deposition, which we will start with glaciers, glacial deposition, I just wanted to review a little bit about glaciers in the past and present. So the current extent of glaciers worldwide is found here. The red are, for the most part, alpine glaciers caused by altitude and the accumulation of snow over the course of a year, which doesn't melt. But the Greenland glaciers and the Antarctic glaciers, which cover those continents or large pieces of landmass, are actually referred to generally as ice sheets, the result of large-scale continental glaciation. So this is the current extent. And all of these areas where you see valley glaciers are shrinking. There's not a single one where the glacial situation shows an increase anywhere on Earth. Now, there are variations that seem to happen along the margins of Greenland and Antarctica, with ice increasing and decreasing in both places. NOAA, our government's atmospheric and oceanic governing body and source of scientific data about the Earth, says this: large continental ice sheets in the northern hemisphere have grown and retreated many times in the past. We call the times with large ice sheets glacial periods or ice ages, and times without large ice sheets interglacial periods. The most recent glacial period occurred between about 120,000 and 11,500 years ago. Since then, Earth has been in an interglacial period called the Holocene. Glacial periods are colder, dustier, and generally drier than interglacial periods. These interglacial cycles are apparent in many marine and terrestrial paleoclimate records from around the world. And we talked about what that word paleoclimate record might mean. That might mean looking at the gases that are trapped in air bubbles that are frozen in ice in cores of ice taken from the ice sheet on Greenland or Antarctica, which go back hundreds of thousands of years. Information from those air bubbles can help us understand what the climate was when that ice froze, however many years ago. We can look at coral, and we can look at cross-sections of coral and how they've grown more rapidly or more slowly based on periods of climatic change. We can look at the history of the climate in tree rings, in trees that have lasted through period hundreds, if not even thousands of years, by not decomposing based on where they have died. So there are a bunch of different ways that science has come up with to figure out what the climate was in the distant past, and thus try to understand these fluctuations between glacial and interglacial periods. I should also say, of course, that sediments and rocks, sedimentary rocks, are very invaluable in helping us understand these shifts, because we can find rocks that were clearly made from glacially deposited sediments. And thus, if you can age those rocks, using radioactive dating, you can have a sense of how glaciation changed over the course of the Earth's history. Now, here we have a series of data that links to what a lot of people think is the cause of this shift between a glacial and an interglacial period over the course of time. And it has to do with the motions of the Earth in relation to our orbit. Our precession, which is how we wobble over a course of 19 to 22 to 24,000 years, wobbling in our as we rotate. Our obliquity, which is how our axial tilt shifts over the course of 41,000 years, and the eccentricity of our orbit changing over long periods of time. And what people have done is put this data together, and this is first proposed by a gentleman named Milankovitch about 80 years ago, maybe 90 years ago now. And Milankovitch looked at these orbital motions and then connected them to glacial sedimentation that was understood to exist in the rock record, and saw that there seemed to be a pattern between the stages of glaciation, very cold glacial periods, and then interglacial periods of warming. Well, this is a very difficult slide to look at, so I thought it might be worthwhile to take a quick look at this little graphic that has been put together by a professor, I think, at the University of Wisconsin. And we can see the Earth going around the sun, and we see here we're at the summer solstice, and then we're at aphelion. We're moving towards the fall. And we can add a little bit of data on the right. Now, really, the motion of the sun in this animation really is of the Earth, is of no consequence. What's really important is to look first at this fluctuation in temperature based on an ice core that was taken. And it goes back 400,000 years, and you can see there's anomalous times when the Earth is much colder, and then the Earth gets warmer. Colder, period of glaciation, warmer, interglacial. Then a long interglacial, then colder again, warm, glacial, to now. We're in an interglacial now. Well, how does that correspond to these orbital motions? Well, first our eccentricity, and you can see that there's a definite connection with eccentricity over this long period of time. Eccentricity changes very slowly, but you can see as the eccentricity is increasing, so too we seem to be getting a period in the interglacial of warming, then cooling, warming, cooling, warming. It seems to correlate fairly closely. Then if we look at this wobble, we can see that it too seems to have a pattern that doesn't absolutely match, but pretty well, the variation in temperature. You can see that the precession also follows that temperature change. And finally, tilt is pretty closely connected. You can see we get a change in our tilt, which then corresponds to this warming. Here, another push-up, and as the tilt varies, we get a cooling. So this idea is quite powerful and is accepted by many people as a cause of this pattern of glacial and interglacial. We also can see a series of lines here that are showing us temperature variation in the red, carbon dioxide in the gray, and methane in the black. And we can see that as carbon dioxide and methane go up, so the temperature goes up. And it's a very direct relationship. And here we see our present increase. So we can combine all of these things in our understanding of what glaciation is and how it relates to forces that are now at work in terms of keeping us warmer, probably for a longer period than might have been expected in relation to the end of our last glacial period, the Wisconsinan, which ended at about 11,500 years ago, and whenever we would have our next one, some several 100,000 years from now. So here is that last glaciation stretching down, creating Long Island. This is a terminal moraine we'll learn about, glacial deposit. Long Island is not there while the glacier is there. Sea level drops, and we can see the border going down. We also see older glaciations. So Wisconsin separated by interstadial period. It wasn't as severe a warming. Then that separated Illinois from the Kansan, another period of glaciation, and then that separated from the Nebraskan, going back several million years, these different periods. And here you got this a little more detail, but I'm not gonna go into any great detail here. I think we'll just jump ahead, and just to show you that we have these periods of cooling that seem to follow a pattern, although you don't see it, as often as you might think you would, given the Milankovitch cycles. But there are people who are studying that, and that is one of the arguments against it. It doesn't seem to, I guess, come up in a graph like this, in a graphic like this. But I wanted to show this just because this shows you the period of what we called snowball Earth. If you remember, we talked about that as a cause for the sudden increase in the amount of atmospheric O2 after this major cooling, which then leads to an explosion of complex life in the Cambrian, invertebrates, marine organisms, which eventually move out of the water. And then we go into our terrestrial and marine ecosystem reality of our Earth. And within that, some periods of intense cooling. Now, of course, with all of this information, we need to find evidence in sediments that have been deposited and turned into sedimentary rock, and that is one of the reasons we don't have probably as complete a picture as we would like in terms of how often the Earth has been cooled to the point of creating a glacial period. I thought this would be just worthwhile to look at. This is the last glaciation, the Wisconsin, and it shows the ice sheet that spreads Greenland over all of Canada down into what's now the United States and into the Europe, Russia, and the Himalayas as the Earth cools. And of course, sea level drops in this period because during a period of glaciation, you are taking water out of the ocean through evaporation at a lower latitude. You are bringing it up into the atmosphere, cooling it, and if that atmospheric moisture falls out over this northern area, that water will stay frozen. It won't remelt and go back to the ocean. So there's a deficit of water that is draining annually into the ocean, and sea level goes down. Once that glaciation stops and you have the retreat of the glaciers, that water starts to go back into the ocean and you get sea level increase. And we saw that the science believes it took from about 11,500 years ago to about 5,000 years ago for sea level to finally rise back after this ice had retreated, to rise back to its current shoreline configuration. And of course, the shoreline configuration is changing now with climate change and increase in sea level as we melt the last bits of ice on the ice shelves or ice sheets of Greenland and Antarctica. This is a image that is just meant to give you a sense of different types of ecosystems that existed in this period of maximum glaciation, the glacial maximum, which was at about 18,000 years ago. That's when the glaciers had reached the furthest point south. And you can see them melting out. And what do you think this became? Well, this looks like maybe an early version of, say, an Ohio River. And here our Mississippi River. And this certainly what was become the Mississippi River. And eventually we have the creation of a big delta system here at the mouth around New Orleans. With that, I think we'll stop and let you enjoy that first video, and we'll continue with glacial deposits in a moment.